In this video, I'm going to go over a stress transformation problem from beginning to end. Since it's a little bit of a long solution, I'm going to split it up into two separate videos. This first video, we're just going to go and calculate the initial stress state at point A, which is 1 meter away from the roller, and in the second video, we'll go over finding the principal stresses and the max shear stresses and the corresponding angles. So let's get started. So the first thing we want to do is just to draw a free body diagram of our system that's given here. And so here is our free body diagram for our system. We've got our 3 reactions at our fixed end and our 1 reaction at our roller. One thing to note is we do have 4 unknowns in this case, and we only have 3 equations, so this is an indeterminate problem. So that's going to be something that we're going to have to figure out later on. So the next thing we want to do, now we have our free body diagram, so we're interested in just finding what the forces are going to be at our section, which is going to be 1 meter away from the roller. So that's going to be our next thing we want to do. And since we have these 4 unknowns, let's do everything in terms of our F1 force, just because that'll make it easier to solve what our internal forces are at our section. So we're going to be making a section cut 1 meter away from the roller. We'll just say it's right there. So that's going to be our 1 meter. And so now we're going to draw another free body diagram of that section cut looking to the right. And there is our free body diagram for our tiny section cut. So now the next thing we want to do is let's get all of our internal forces in terms of our 1 unknown in this case, which is going to be our F1 force. So our first thing is just going to be our sum of the forces in the x direction, and when you do that you should get that your internal force P is just going to be equal to your 200 newtons. When you do the sum of the forces in the y direction, you should get that V, our shear force, is going to be equal to a negative F1. Since they're going in the same direction, it has to be negative. And then lastly, our moment, when you take the sum of the moments, you should get that that is going to be equal to F1 times the moment arm, which in this case is 1 meter, minus, sorry, not plus, minus our applied moment at the end, which is 50 Newton meters. So those are our 3 internal forces in terms of F1. Now we just need to find what our F1 force is going to be. And so to do that, we need to deal with the fact that we have an indeterminate problem. And so the easiest way to do that, and how I'm going to go over it in this solution, is to do superposition. So we're going to split our system into 2 separate systems to analyze it. So I'm just going to draw those really quickly. So these are our 2 systems. So if you add them together, you'll get what we have in our original system. So what we're looking at is that we're going to compare the deflections of both of these. So we know that the deflection at a roller support has to be 0 because there can be no vertical deflection at a roller support. So we're saying, okay, if we just have our first system, which is just our applied loads, and have that deflection plus our deflection just due to the reaction force at F1, that should give us no deflection. So we can say that U1 plus U2 is just going to give us 0. So that's going to be our relationship so that we can find F1. So now you should have available to you what the deflections are going to be of a cantilevered beam at the end of a cantilevered beam due to a force applied and also a moment applied. So our 200 Newton axial force that is applied on our first system, that's not going to cause any vertical deflection, so we can kind of ignore it. So if we look at U1 first, so what's that going to be? So that's going to, when we have an applied moment like that, it's going to give us a vertical deflection that's actually going to be going down, and the value of that is going to be a negative ml squared over 2EI. So you should be able to just get this equation off of your equation sheet, or you can look it up online. This is just for a cantilevered beam with a moment applied at the end. And so we'll do the same thing. So for U2, the deflection on our second system is just going to be equal to some force times L cubed over 3EI. So these are both for a cantilever. So now that we have those two equations and we know the moment that's applied and we are trying to solve for F1, we can plug those into our equation and solve for what F1 is going to be. So when you do that, you plug those values in. The EIs end up canceling out and you plug in the length as 4 meters. You should get a value for F1 that is going to be equal to 18.75 newtons. So now that we've found F1, we can go ahead and plug that into our internal forces equations that we had found earlier and figure out what the internal forces are at our cross-section. So now our new internal forces. Our axial force is still going to be 200 newtons, that hasn't changed. Now we know our shear force is a negative 18.75 newtons. And we know our moment, when you plug F1 back in, is going to be a negative 31.25 Newton meters. And this is for, if we take our beam, and this is where our cut is, this is going to give us a shear that's actually going down, a moment that's also going down, and then an axial force that's going outward. So this is going to be our P, our M, and our V. And this is our F1. So these are the actual directions based off of the positives and negatives that are going on in our internal forces that we found. So if that's the actual direction, if we now instead flip it to look at the other side of the cut, we have to flip those forces as well. So I'm going to draw that really quickly. So here is what our internal forces look like on the other side, the other cut face. Now we can see where our point A is going to be looking at. It just makes it a little easier to look at. So now we have, you notice we have our shear force going up, that's going to be 18.75 newtons. We have our moment that is applied right along the same axis about where A is also located, and then we also have our axial force. So if we were to just write down our equations for stresses that we're interested in, our axial stress, our normal stress, that's just going to be a force over an area. We also have a shear stress that we're interested in, and so that's going to be equal to VQ over IT. And then we actually, in this case, don't have a stress due to the bending moment, since our bending moment is since the stress that we're looking at, since the stress we're looking at is going to be on the same line that the moment is bending about. So if we look at our equation for stress due to bending moment, my over I, in this case, our y, or our distance away from the neutral axis, is going to be 0. So that just means that our stresses are going to be 0 due to the bending moment. But we will still have an axial stress and a shear stress at point A. So now we just need to find our section constants, like our area, our moment of inertia, and our thickness, and the Q value, in order to figure out what our stresses are going to be. So I'm going to redraw our cross-section really quick. Okay, here's our cross-section. So now we'll solve for our area first. So our area is just going to be equal to our 50 millimeters times our 10 millimeters. So that's just going to be equal to 500 millimeters squared. Next is finding our I value. That's just going to be, for a rectangle, it's 1/12 BH cubed. So it's going to be 1/12, our base in this case is 10. And our height is 50. So that's going to get us a value of 1.04 times 10 to the 5th millimeters to the 4th. Our next value that we're going to find is our thickness. Our thickness is going to be the length of the cut we make when we're looking at shear stress. So since our shear stress is going up and down in the y direction, our cut is perpendicular to that. So our cut right at A is going to be this length, which is just going to be 10 millimeters. And then the last thing we want to find is our Q value. And our Q value is going to be the area of our cut off section, it's called A star, times Y bar of that cross section. So if I was to draw it, this is going to be the area that we're interested in. So that area is just going to be 10 times 25. So that's just going to be 250. And then our y bar in this case is going to be the centroid of this section. It's going to be the distance from that to the centroid of the current section, which is at 25 millimeters. So that's our y bar. So our y bar in this case is just going to be 25 divided by 2. So that's just going to be 12.5. So if you multiply those two values together, you'll get a Q, which is equal to 3125 millimeters to the third. So now that we have all those values, we can go ahead and solve for what our stresses are going to be. So let's start with our axial stress to begin with. So our axial stress is going to be sigma xx, since x is the axis that is running perpendicular to our cut face. So that is just going to be equal to our axial force, which is 200 newtons, and it's positive because it's pointing outwards, which means that the section is in tension. So that's why it's positive, over our area, which is 500 millimeters squared. So that's going to get us a value of 0.4 megapascals. So I didn't do the unit conversion, but a kilonewton per millimeter squared is a gigapascal, so that means a newton per millimeter squared would be a megapascal. That's just a little tidbit of information to know. If you don't feel comfortable doing that, you can always put everything in terms of newton and meters and then convert to megapascals later. But for this solution, I'm just going to convert from newton per millimeter squared directly into megapascals. So that's going to be our value for our axial stress. Now the next one we're looking at is going to be our shear stress. So the first thing we want to do is figure out the subscripts. Our first subscript is always the same since our cut face is still facing in the x direction, so that's going to be an x. And since it's also facing the positive x direction, that's going to be a positive for our first subscript. And now the second subscript is the direction of the shear force. And in this case, it's going in the positive y direction. So that's going to be our second subscript. So now we just need to plug in our values. So our shear force is going in the positive y direction. So it's a positive shear force, which in this case is 18.75 newtons. Our Q in this case we found to be 3125 millimeters to the third, over our I, which is 1.04 times 10 to the fifth millimeters to the fourth, times our thickness, which is 10 millimeters. So that is also going to get you, when you cross out all the millimeters and is also going to get you a megapascal as your units in the end. So that's going to give us 0.057 megapascals. So the last thing I just want to show you is to show you this exact thing in matrix form, and also to show you what it'll look like on the cube, on what it'll look like on the stress cube. So here is what this stress profile looks like in matrix form, and also on a 3D stress cube and just a 2D stress cube.